Okay, let's take some time to talk about power and efficiency. So let's start with this idea. We've got a barbell here with a lot of weights on it. And somebody's going to go ahead and lift it a height of 0.75 meters in a time of 1 second. And let's assume that they lift this barbell at a constant velocity. And so, for instance, if this were a 300-pound dumbbell, then the force upward they'd have to lift it at would be 300 pounds because it would be constant velocity lift. Well, after that person lifts it, another person comes along. Instead of lifting the same weight in 1 second, this person lifts it in a half of a second. And they lift the same weight, they lift it at constant speed, and they lift it the same distance, the same height. The question becomes, what's different about these two situations? The one where the person lifted it in 1 second, and the one where the person lifted it in a half a second. What's different? Well, first of all, I want to point out that the work that was done is the same. In each case, the work is the same. Why would that be? Because in each case, 300 pounds is exerted upward to lift it at constant velocity, and it's lifted the same distance. In each case, force times distance gives the same amount of work. But what is different is this time frame in which it's done. And when the time is different, we would say that the power output is different. Technically speaking, power is going to be work divided by time. And if you consider the units for these quantities, I have work over here, and work is measured in joules, as you know. We've got time right here. Time is measured in seconds. And so it looks like power is going to be measured in units of joules per second. And if you consider what a joule is a kilogram meter squared per second squared. But if you're going to divide by seconds, now that instead of seconds squared, that's going to become seconds cubed. So here's what a joule per second is. It's a kilogram meter squared per second cubed. And there's a name for that. We call that a watt. And the SI, or System International unit for power, is going to be the watt. You've heard of that before, like 40-watt light bulbs, 60-watt light bulbs, or maybe your hair dryer is a 1200-watt hair dryer. They're talking about units of power. So at its core, power is work divided by time. In the case where the barbell was lifted quickly at 0.5 seconds, the power output would be greater, be twice as much, because the time was cut in half. So just to show you how this equation works, let's just suppose we have a 4 kilogram mass that we're going to lift upward at constant speed. We're going to lift it at a distance of 3 meters in a time of 2 seconds. We want to calculate the power output. Well, power is work divided by time. As you know, work is force times distance, and then we divide it by time to get power. You might be wondering what happened to the cosine theta. Can we just ignore that? Well, in this case we can, because it turns out that the distance that this is lifted, or the displacement I should say, and the force with which it's lifted, they both are in the same direction. So the angle between them is 0, and cosine of 0 is 1. So we can kind of forget the cosine theta here. But let's consider the forces. If I've got a 4 kilogram mass, it's about 40 newtons. I'll just use G equals 10. And if I'm going to lift this thing with constant velocity, I'm going to need some sort of lift force, which is going to be equal to 40 newtons to lift it at constant velocity. And so when I go ahead and do my power equation, I'm going to have 40 newtons of force times a distance of 3 meters divided by a time of 2 seconds. If you do that, you get 6 watts. Or you could say 6 joules per second is the power output. Now I want to throw a word at you, and I'm going to throw this word rate. Rate means divided by time. So if you found the rate of change of velocity, you'd be talking about acceleration. It'd be change in velocity divided by time. If you found the rate of change of distance, that would be, or the rate of change of position, that would be velocity. Change in position divided by time. Well, what is this here? Well, this is the rate at which work is done. The rate, check it out right there, the rate at which work is done. And anytime in this unit, this energy unit, that you hear the word rate, you can bet your bottom dollar that they're talking about power. So as soon as they say the word rate, pull out the power equation and start calculating. Now back to this example, if we took this time and instead of 2 seconds we did it in 1 second, we'd be cutting the time in half, and so the power output, 6 watts, would be doubled to 12 watts. So you can kind of see how that works. The shorter the time, the greater the power output. Now there are other units for power. In fact, there's this unit called the horsepower, or just 1 HP. Horsepower, 1 horsepower is equal to 746 watts. So you probably have to use that in a problem or two. So just know there's a relationship there between watts and horsepower. They both measure power, they're just different units. Kind of like meters is to yards as watts is to horsepower, or something like that. Now let's investigate this power equation a little bit more carefully. We said power is work divided by time. Well, work, don't forget, is equal to change in energy. So we could just as easily say change in energy divided by time is power, or the rate at which energy is changed, or the rate at which energy is transferred is power. Think about this. If you were to take a rock and lift it upward at constant velocity, what you're doing is you're changing its potential energy. So we could write power kind of like this: mgh minus mgh initial, and then divide that by time, and you have the power that took place during that lift. Or suppose for a second that you had a car that was like this, and it was going from 0 to 60 meters per second in a certain amount of time. Well, now you're not changing its height, but what you are changing is its speed. So instead of a change in potential energy, we would have a change in kinetic energy. So the power equation would look like this: 1/2 mv squared minus 1/2 mv naught squared, all divided by time. Of course, you could be talking about spring energy, and you can do 1/2 kx squared minus 1/2 kx initial squared divided by time. Anytime you have a change in energy and you divide by time, you have the rate at which energy is changed, or the rate at which energy is transferred, which is power. So when you see a question they're asking about power, always ask yourself, are they changing the height while it's moving at a constant speed? If so, use that. Or are they changing the speed? If so, use that. Here's another cool way to think about power. We said power is work divided by time. So watch this move. Work is force times distance, as we've already shown. And then you divide by time, and then I want you to consider what I'm circling in yellow. That right there, distance divided by time, is like average speed, isn't it? So I could rewrite the power equation look like this. Power is force times an average speed. And that's another way to calculate power. And that's kind of a useful way. Let's say that this box is being pushed on by a certain force F, and they wanted to know how much power was generated by that force F. And there may be some friction down here that would cause this thing to move at constant velocity. Maybe we would have friction like so. But if you want to find the power generated by that force F, what you would do is you would plug it in, and then you would just plug in the velocity that the object was moving at, and you would find the power generated by that force F. Of course, in this case, we said it was traveling at constant velocity, so these two forces should be equal, so you could also find the power generated by the friction as well. And for that, you'd get the same thing. Let's consider a situation where a person of mass 80 kilograms is running up the stairs here at constant speed, and by the time they get to the top, they would have traversed a height of 4.1 meters, and they do this in 3.3 seconds. What would the person's power output be? Well, what you can do is you can just think of it in terms of work divided by time, but work is also change in energy, so let's go ahead and just write that. Change in energy divided by time. Because we're changing our height and not our speed, we would go ahead and do mgh minus mgh initial, and if you call this the 0 mark down here, we would say mgh initial would be 0, so it would just be mgh divided by time. If you go ahead and plug in some numbers here, you have 80 times, let's just use 10 for g right now, and the height is 4.1, and you divide by time of 3.3, what do you get? about 994 watts. So as this person is going up the stairs, they're exerting 994 joules every second, or they're actually burning off that much energy every second. 994 watts is 994 joules per second. How many horsepower is this? Well, you can go ahead and say 994 watts, and you know that there's 746 watts in 1 horsepower, and so you can just take 994 divided by 746 to get 1.33. So basically this person's running up the stairs with a power equivalent to 1.33 horses. I don't know if that's the actual meaning of horsepower, but we would say that the person had a power of 1.33 horsepower. Let's take a moment and consider how trigonometry might be worked into a situation like this. Let's say that you've got some skiers that are they're going 100 meters up a tow rope. They're holding on to this rope that pulls them up the hill, and maybe there's a 30-degree angle here, and you want to find a power output. Well, when you think of power, you think of work divided by time, or change in energy divided by time. But if you're moving up this hill at a constant velocity, you're not really changing your velocity, you're changing your height. And so again, we're kind of looking at this mgh over t type thing. And you might not be given the h, but what you are given is the hypotenuse and the angle. So you can know that h here would be 100 sine 30. And that would be your height that you could plug in there. And of course, if you were given a time to get to the top, then you can go ahead and calculate your power, as long as you know your mass. What's interesting is I've seen some problems before where they say where the tow rope is pulling them up at a speed of, say, 3 meters per second. And what you could do with that is you could figure out, it's kind of an interesting approach here, you could figure out the y velocity right here, and you can say that would be 3 meters per second times sine of 30. That'd be 1.5 meters per second. And now what you have is 1.5 meters of height every 1 second. And right there you just plugged in h and t, which is kind of a nifty move. If you multiply by m and multiply by g, then you've got the power output. So just some things to look out for. One other thing you guys got to be told about is a concept called efficiency. Efficiency, and what we're going to say efficiency is this. It's useful energy out divided by energy in. And that's always going to give you a decimal, like 0.6 or 0.44 or 0.7. If you want to report it as a percent, you can just multiply by 100 there, and you can actually talk about efficiency being in terms of percent, like 60%. How does this work? Well, let's say that I had a light bulb, okay? And a light bulb's mission in life is to create light. And let's say that I had coming in to this light bulb was maybe 100 joules per second of electrical energy. And coming out of this light bulb was not 100 joules per second of light energy. Maybe it was only 70 joules per second of light energy. And so what happens, this 70 joules per second, you know, it sounds like it's an energy because you hear the word joules, but it's really a power. So just so you know, this equation could be written as power out divided by power in. But you can think of it in terms of energy out divided by energy in also. But you've got 70 joules per second coming out, but you had 100 joules per second going in. And so, you know, the efficiency here is going to be 70%. And what that means is that the light bulb is only doing a 70% good job of taking electrical energy and turning it into light energy, useful energy out. The other 30%, the remaining 30%, is turned to heat. That's kind of how efficiency works. An automobile engine might only be 40% efficient. So what that means is it takes, out of all the joules of gasoline that gets put into it, only 40% of those joules end up being kinetic energy, you know, that's changing the velocity of the car. The remaining 60% is all turned to heat in the engine. So this is what efficiency is, and that's how it works. So there you have it. That's power and efficiency. At this point, you're just going to have to really practice some problems in order to understand these concepts well. So go ahead and give some problems a try, check the solutions, and good luck. Over now.